This is a video for pre-calculus class. The law of sines and cosines are applications worksheet number 2, the selected solutions that were asked for in class. So to begin with, problem number 5, we had started setting this up in class, but here's a better rendition of it. There's a river, and there's two sides of the river, two banks on the river, and on one bank there's a tree, and at the base of the tree there's a guy standing there. And the guy is standing there, and eventually he's going to climb to the top of the tree. And when he climbs the top tree, he's going to be looking at a spot across the river. So if you look at this right now, that there is a spot, the spot right here that he's looking at, that's directly across the river from him. And when he climbed to the top of the tree, we know that the tree is 10 feet tall, so the distance from his line of sight from when he was standing at the base of the tree to when he's standing at the top of the tree is 10 feet. He then looks at that spot, and from his line of horizon, he's looking down, so it's an angle of depression. He's looking down 12 degrees when he's standing at the base of the tree and 15 degrees when he's at the top of the tree. The question in the problem is, how far is this boy from the other side of the river? So we're looking for that segment A, the length of A. The other question that's going to be asked is, how wide is the river? To figure how wide the river is, I want you to look at, I put a line that's going straight up from that spot that's perpendicular to the boy's line of sight. So this is kind of like a pole that would be going straight up on the bank of the river. And his line of sight intersects that at a 90-degree angle. And the width of the river would be how far his line of sight is to that pole. If you're not quite sure, you say, well, I don't see how that's the width of the river, that I could do the same thing. I could draw a perpendicular from the spot to his feet, or to the river bank, exactly, such that it was 90 degrees, again, perpendicular. And now if you look at this, what I've created is a rectangle where opposite sides are B, and the other opposite sides would be the boy and this height from perpendicular height from the spot up to his line of vision. And A, the distance from the boy's head, his face, to that spot would be a diagonal of a rectangle. Main thing is, we're here to solve for the measure of A, the distance from the boy to the spot, and the distance of B, which is the width of the river. Let's look at this just with regular triangles now. Okay, so here I've taken that situation and just drawn it as a simple triangle. P stands for when the boy is standing at the base of the tree. T is when he's standing at the top of the tree, and S is that spot on the other side of the river. We know that his angle of depression is, we've got that 12 degrees and 15 degrees, so that allows us to come up with the two angles there, 75 degrees, because we would just, because 75 and the 115 would create the 90 degrees to his line of sight. And the 102 happens to be a 90-degree angle plus the 12-degree depression that he's looking at. We need to figure out that third angle. We just use triangle sum theorem. We find that that's 3 degrees. Note then that my drawing is not to scale, and typically they're not going to be to scale when I start these out because I'm not going to redraw it to scale. 3-degree angle is so small I wouldn't be able to draw it very well. The first thing we're going to try to solve for is this distance A, from the boy that's standing on the bank to the spot across the river. We've got all 3 sides and we do not have all 3 sides. We have 3 angles and 1 side, so that allows us to use the law of sines. Remember, you can pause the video at any time if you're not sure, want to look at these equations more. I'm going to plug that in to my calculator and write down many decimal digits, okay? Know that I'm going to round it to just 1 decimal digit, but I need to know the whole thing. Or not the whole thing, but at least 4 to 5 decimal digits that I'm going to use later on in the problem. So now I know the distance from the boy to the spot is 184.6 feet. Now we need to move on to the other part, the width of the river. So I'm going to start back with that same triangle, getting a look at it. And remember that I did a perpendicular up from the spot, and then I went and looked at his line of sight. So really the triangle we're interested in this time is just this small little triangle, so I'm going to get rid of that. And we can see then that that angle is going to be 12 degrees, his angle of depression when he was looking down to the spot. And we've solved for A. I have an A in there, but we know right up above we can see what A is. And this is a right triangle where I'm looking, I have the hypotenuse of a right triangle, and I'm trying to find the side B, which is adjacent to the 12 degrees. So if you think about that, I have the hypotenuse, I have the angle, and I need the adjacent. Well, what links adjacent and hypotenuse? That's cosine. So I simply am going to do right triangle trig. I'm not going to even use law of sine or law of cosine for this part of it. And I plug in, I solve for B, which is the distance of the river, the width of the river. Plug in my A, and I'm going to use several decimal digits when I use the calculations. And then my final answer will only be with one decimal digit, with one place. And so I've got the width of the river, the width of the river is 180.5 feet. The next was a problem about Grand Canyon. You've got somebody at point A looking across the Grand Canyon at another location, point B, straight across the Grand Canyon. It's due east, or right across it. I don't know what they said, but right across. And then there was another location, I don't know if it was a person or what, I can't remember, but there's another location, C units away from A. And we were told that C is 200 yards from A. So what we want to find out is the distance from the point A to point B. So it's kind of like asking you for the width of the Grand Canyon. I don't know if anybody's ever been to the Grand Canyon, but I was always shocked at this, actually. And the difficulty of this problem, it's not really the situation, it's that they're going to give you the angles in degrees and minutes. And whenever we have minutes, we just divide it by 60, and that will give us the decimal degrees. We'll get a decimal answer there. So that's what we need for our problem, and we're going to do that with the other angle that they gave us. Now we have our decimal degrees. And this becomes a problem where we've put in the angles, and we can find the third angle if we want to, but the main thing is we have all our angles in one side, use the law of sines, and we can solve, and don't forget, use a lot of decimal digits whenever you're calculating so you don't have an error, and then round your answer to the nearest tenth. And so my answer is 166.6 yards across the Grand Canyon. Wow. Okay. Next problem, I believe this had to do with people on the shoreline in a boat or something, and two people that were half a mile apart looking out at some location. And again, it had it had degrees and minutes, so we had to change it to decimal degrees. And so that was really the issue, I think, for some of you when asking the question. Because then we put in those decimal degrees. We've got them in decimal form. We have the angles, so we can find the third angle. So now we know we have all three angles, and one side easily lends itself to law of cosines, where we want to find the sides A and side B. So for side A, we have the law of sines there, and we calculate it out, and we get that. And don't forget, we're going to round it to the nearest tenth. Well, that's half a mile. Interesting. And the second problem, we're going to do that one out, and we get, when we round that distance, we also get a half a mile. Now, it is not true that this is an equilateral triangle, although all three sides rounded to half a mile. The three angles are not 60 degrees, but the rounding. So I want you to realize here, this is how come, with rounding, and we don't really get that accurate, because it's not true that all those lengths are exactly half a mile. One of them is definitely shorter than half a mile, one of them is definitely longer than half a mile, and one of the distances, the one that was given, is a half a mile. So, be aware of those issues with rounding. Problem number 3. Oh no, we had two people. Person A, and they said they were looking due east, and they were looking up at the sky at a UFO. And exactly 1 mile to the west of them, so behind them, point B, is another person looking up at the UFO. There it is. Aliens. And they're both looking up at the alien. Person A is looking up at an angle of 40 degrees. Person B is looking up at an angle of 25 degrees. We've got our adjacent angle to the 40, so we know that angle in there is 140. We can calculate that the angle the alien is staring between the two people is 15 degrees. We've got all three angles and one side. It lends itself to the law of cosines, in which they're asking us to find the distance from person A to the alien. On top of that, they are going to be asking us for how high up is the alien. So how high in the sky is the alien? Or they say UFO, but we can see it's an alien. We use our law of sines and solve for x, plug it into our calculator, and then round it to the nearest tenth. But remember that we're thinking of that, we've got the whole number written somewhere, it's in our calculator, because we're going to need to use that x, that value, to solve for the h. Because now we see, oh, it's just a right triangle, so the same thing. We don't need law of sines or law of cosines. We're just going to use right triangle trig, that the sine of 40 is the h, the height to the alien, which is actually the side opposite, and x would be the hypotenuse here. And so now this time, remember, we're not going to just plug in 1.6. We need to plug in more decimal digits of that, that length. So we're plugging in 1.632887. You could plug in even more if you'd like. And we get that the height is approximately 1.04959, which rounds to one decimal place to just 1 mile. We know that it's actually a little bit more than a mile, but it rounds to 1.0 miles. For problem number 4, there's a building that has a flag on it. And there's the flag, it's Kimco. And there's a person standing 400 feet away from the building. The person's looking up at the base of the flagpole, and then they're looking up at the top of the flagpole. From their line of horizon, their line of elevation, their angle of elevation is 60 degrees to the base of the flagpole. Looking at the top of the flagpole, the angle of elevation is 62.5 degrees. Doing a little bit of subtraction there, we can find that that angle is going to be 2.5. What we're asked to find is the height of the flagpole. But if you look at that triangle that's created by the person looking at the base and then the person looking up at the top of the flagpole, we don't have any lengths at all. We could actually figure out all 3 angles with the information given, but that isn't enough because we need to have at least one length. So the one length that's given in the problem is the person is 400 feet away from the building. And we go, oh, wait, there's a right triangle right here. This creates a right triangle. And I can find the value for y, because I can use the law, not the law of sines, just plain old trig, right triangle trig, and that cosine of 60 degrees is equal to 400 over y, because we've got the adjacent and the hypotenuse. We solve for y, and we get 800 feet. Obviously, this picture is not drawn to scale, because 60 degrees is the larger of the 2 acute angles, where this is a 30, 60, 90 degree triangle. So obviously this is not drawn to scale. And the adjacent angle to the 30 degrees is 150. And so now to solve for the height of the pole, which is really what our goal was, I'm going to look at this other triangle. And in this triangle, I notice that I get my third angle from doing some little subtraction there. I have all 3 angles, and I now have the measure of y, which is 800. Since I have at least one side, I can use the law of sines. And I can see that I've got x equals y times sine of 2.5 divided by sine of 27.5, and I have my y as 800. So plugging that into my calculator and then rounding to the nearest tenth, I have 75.6 feet. So that's the end of the selected problems on the first page. And for your pleasure, here we have the drawing of an alien. And this is going to take way too long, so we're just going to skip there and, help me! That's the end of this video.